Just so you know, we have uh, 9 students in the class, and I prefer not to actually get going until we have at least 5 out of 9. So if you're simply not going to attend live, either in person or virtually, all I need to reject that. I can't even tell who that's from. Okay, that was eerie. I reject attended at all. Like I'm in person or virtually. Please let me know, and if you are going to attend, then please try to come on time. So okay, now okay, but probably could have started earlier, but again, I'd like to have at least a quorum before I do. And I'm sorry, it's probably a problematic work of mine, but it's it. But so I apologize for the delay. That's my choice, but based on what I have in the notes, I think we can still get through everything before before we schedule that. Well, I guess it depends on how many homework questions we have. Well, I guess we have fewer people around to ask homework questions, so see how that goes. First, some announcements. So I've had to make some changes to the schedule just because of not having class last Thursday due to the football game. So we may have won the game, but lost the day of class. So, and not being able to take it into account when planning at the beginning of the semester, thanks to administration, who totally could have avoided that situation. Things had to be tweaked. Here, and I've not yet updated the schedule on my own site, but I will do that after class to reflect what I'm announcing now. So first, I'm going to. It sounds like I'm making things worse for myself, but in the end, it'll make things better for everyone. And that is a response to canceling one class by the administration by canceling another class myself. And that is, there will be no class on Tuesday, November 22nd, because that is like pretty much the hour before Thanksgiving break begins. And I think just, still having class right before that is just mean. So, okay, and then another adjustment I will make is I'd have to, because of last Thursday, I'd have to lose a topic anyway. What I'm doing is I will not be covering chapter 18 anymore. I'll be ending with the chapter 15 material that I'll be starting today. So as a consequence, homework 12, which has not yet been posted to Canvas anyway, will be deleted. So therefore, but because I'm sticking with the previous editions of graduate students have lowest assigned homework grade dropped, and then undergraduates have the lowest 2 homework grades dropped. So undergraduates must complete 9 out of 11 homeworks. So to answer your question, that's how many assignments you have. 9 total. Stop calling me. Graduate students must complete 10 out. All right. Now, so one way to look at it is, for instance, if you are, okay, I guess I can also formalize this. So let's suppose that you're a graduate student. So therefore, you have your one of the 11 assignments dropped. You submit the other 10. So then it works out pretty nicely that a graduate student can obtain an A overall by acing 9 homeworks. So, because generally the homework rate's been pretty high. There's been quite a few hundreds. So a graduate student who gets 9 grades of 100 can just stop because they have an A. And similarly, an undergraduate aces, and so my formal definition of ace is greater than 100 or above. 8 homeworks will also have an A, because that would be, 8 out of 9. Now, that translates into 88.9%, but I'll just give the boost. So, okay. So, if you don't have that many hundreds among your assignments, but if the average across the 9 is high enough, then also will be an A. Okay, so yes, so really what that means is I'm obligated to therefore use that as at a minimum as a cutoff between a B and an A instead of a traditional 90 or 89.5. I've heard there's some professors, like in other departments, who they won't round up. Like if you get for instance an 89.6, then they'll give you a B. And I find that offensive on multiple levels, mathematically and just from a quality standpoint. So that's how they roll. But so I'm basically using this as a cutoff for. All right, good. So I guess that's the undergraduate cutoff. I guess for the grad student in this territory, I know we're between this. Okay, I'll give it to him. I've often played fast and loose with the cutoffs. I mean, if someone is that close. Okay. All right. So that's the situation as far as assignment. So as far as the schedule of topics, I'll have to update my own site for that, so I'll take care of that after class. Okay. So what that means is, as far as the schedule is concerned, okay, so I'm covering 15.1 today on November 1st. It basically shifts everything prior to Thanksgiving. Okay, so for 15.4. Okay, so that means that after Thanksgiving, we have 1 week of class. That's November 29th, December 1st. But I will only have 1 section to cover, and that is spherical harmonics. That's 15.5. So that means that we might have a class period left over. I guess I can use that as a homework if anybody has more questions. We've done that before. So okay. So that means that so last topic that will be on Tuesday, 5. Okay. So the homework questions only on that Thursday. Okay. Oops. Okay, so are there any questions about what has been done here? Sure, everybody knows what they need to do.
So the official last class be the November 29th and December 1st exam.
Yeah, I mean, I'll be here to conduct class, but, yeah. Yeah, well, I guess last time I did that, we had 2 students show up and ask questions.
I mean, considering there's no exam, so
Right.
technically that would be the last day, but
Yes.
it's not, so.
I won't show up. That one, just so you know.
Sorry, what?
I won't show up for the first one, because I have a flight, so
Works perfect for
it
you.
worked out.
All right, yeah, so, also, last time we did that, I had the question say, you were traveling then, so you wouldn't show up anyway. So,
So 2 people show up.
Yeah, I think I did show up last time. I don't know.
yeah, you did, you and one other.
Yeah.
So,
Maybe I should
if you have questions. Okay. All right, well, so, okay. Okay. Cool. All right, so we're good to. Okay, so here we go. So now it's time for the final chapter. But before I get into that chapter, there's a few things that actually occur in sections that I have not covered, that I need to satisfactorily explain everything in what we'll cover. Okay. Okay, the first is this is a fundamental theorem from complex analysis, Cauchy's integral formula. So if we have function f(z) that's analytic, by analytic can be expressed in the conversion power series, at least locally. So certain functions you're familiar with that have Taylor series, like the exponential, sine, cosine, or it may have a conversion power series that has a finite radius of convergence. So that's like locally analytic. So the analytic function on a closed contour C, so a closed curve in a complex plane, and if it's analytic on that curve and in the interior, it's very important. And we're assuming that the curve C has counterclockwise orientation to get the sign correct. Then your function f can be represented using this integral. So it's interesting that I'll actually want to make sure I have all my assumptions stated correctly. Cauchy's integral formula that is covered in okay, actually from chapter 11, which is a chapter I skipped. Okay. Okay, so I have to make clear that z naught, the point in which you're evaluating function, is the point in the interior of the closed curve C. So it's interesting that the value of f at some point inside the closed curve can be determined entirely in terms of values of f on the curve. but it's because of f of z having this power series representation that makes that possible. The real definition of analytic is that it's differentiable and single valued in a region of a complex plane. Another characterization would come in that locally convergent power series. All right. Now, one nice thing about Cauchy's integral formula is that we have this now have this expression for derivatives of f at a point. So all I'm doing here is I'm taking the Cauchy integral formula and I'm just taking its derivative with respect to z naught, but the only dependence on z naught is right here. So if you think of this as f of z times z minus z naught raised to the -1 power. So if I'm taking a derivative, all I have to do is apply the power rule to this denominator n times. So I get a factor of n factorial up front, and then I have z minus z naught raised to the n plus first power in the denominator. So it gives a very simple expression for the for a derivative. Now, I'm only introducing this because I'm going to use it in a little bit for the next slide. So this is back to something that we've seen before. We have an eigenvalue problem involving a second order ODE. Although notice that there's no coefficient of y here except for this this term involving the eigenvalue lambda. So so it's a special case of the eigenvalue problems that we've seen before. That makes it a little easier to solve. Now, this differential operator, py double prime plus qy prime, is not necessarily self-adjoint. The only time it's self-adjoint is if q happens to equal p prime. Now, if it's not the case, now this is something we've seen before. If we multiply this equation by a wave function w of x, where this is a formula for w of x. So this is the same formula for wave function that we saw previously. It's just expressed using different notation. Then we have a self-adjoint operator. And that leads to this formula, a very useful formula called Rodriguez formula for the eigenfunctions of this problem. That if we take the wave function times the coefficient p of x, where p, only p, is raised to the nth power. Then we take its derivative n times and then divide that by the wave function. That's an eigenfunction of this problem. This is very useful for characterizing certain families of orthogonal polynomials that are solutions of an ODE like this. And that's actually the subject of the current chapter. Chapter 15 is all about Legendre polynomials, another Legendre function. But it can also be used to describe, like for instance, Bessel functions. Right. So, so the Rodriguez formula for certain orthogonal polynomials is handy in a lot of situations, as you'll see in certain homework problems. Because suppose p of x is a polynomial of a certain degree, like for instance, let's suppose it has degree 2, like a quadratic. They'll raise it to the nth power, So let's say it has degree 2n. Now let's suppose that wx is a constant, like suppose it's 1. Then you differentiate it. This expression that had degree 2n, by taking the derivative n times, now has degree n. So we end up with a polynomial degree n. So now, suppose I represent this part, w times b, using the Cauchy integral formula, and I use the fact that I can represent derivatives using the Cauchy integral formula. Then I have this integral representation of my eigenfunctions. That's all I've done. I've just applied the Cauchy integral formula to compute this n derivative of this. So notice we have wp to the n playing the role of f right here. X is playing the role of z naught, where we're evaluating function. And this is called, and I really don't know how to pronounce this, the Schleifli integral. Say that a few times fast. We'll go with that. Schleifli integral. I've literally never had to say that out loud before. So when I last taught this class in 2013, I just plain forgot to cover this. So we have this way of representing the eigenfunctions. Now, that is going to be useful for the next thing I'm going to cover, and that I'll need from the current topic. Generating functions. We've seen generating functions before to just, first I showed how they can be used to get a formula for Fibonacci numbers, but then I showed how they can be used to obtain properties of Bessel functions, because I actually showed you the generating function form of Bessel functions. Now here's what I failed to do back then, because I just left it out. I did not explain to you back then how you actually got the generating function form of Bessel functions, because you think that there would be some way to derive it using a Bessel equation, which the Bessel functions are solutions of. But I didn't do any of that. I'm doing it now, just in general. So here's our general notion of a generating function versus a sequence of functions fn of x. That could be, for instance, the Bessel functions or whatever other sequence of functions you want. So it's a power series in T, and the coefficients of the power series are functions of x. Now, suppose I want a generating function for the set of solutions to an ODE, such as the Bessel equation or the Legendre equation. What I can do is, if I'm dealing with an ODE of this form, then I have this formula for the solutions in terms of the coefficient of the ODE and the weight function for that ODE. So what I can do is I can substitute this for fn of x. And that is how I get my generating function. So the generating function comes from the coefficients of your ODE, P and Q, because P and Q together give you the wave function, and then I have P again here. So that's all I need to obtain the generating function. So this is a power series in T, and the coefficients of the power series are the eigenfunctions of this differential operator. So, given an ODE this form, you figure out the wave function. And what you can do is, if you're able to work out this integral directly, then even though you don't know any of the solutions of this ODE, you can still get the generating function. So now we're actually starting chapter 15. So here's the ODE we're going to apply all this to, the Legendre equation. So little p of x is 1 minus x squared, and then little q of x is minus 2x, which happens to be the derivative of 1 minus x squared. So what's nice about this ODE, unlike the Bessel equation, it's already self-controlled. Now, I brought up this ODE before, like no problem. So if you look at these notes, it was found to have solutions that are polynomials, and those are called Legendre polynomials. But what you can do is, if I use this as little p and minus 2x little q, and get my weight function, well, it turns out the weight function, because q is equal to p prime, the weight function turns out to be 1. So that works out nicely. So if I fill in all of this, then I can plug all of these things in here and work out the integral, which I won't take the time to do here. But what you get is this function right here, the 1 over the square root. That's the generating function for Legendre polynomials. So this has a power series in T. The coefficients of a power series are Legendre polynomials. So now that we have the generating function, and I've at least given you, I haven't given you all the details, but I've given you at least a path on how it can be obtained directly from the Legendre ODE, we can use this to obtain properties of Legendre polynomials. Before I do that, are there any questions up to this point? So in general, given an ODE of this form, so a general workflow here is you use the coefficients p and q to get w. You try to work out this integral. That gives you the generating function. And then you can work with generating function to learn about your solutions. Now, in the case of Legendre equation, it is possible to get the solutions using Frobenius' method. That's what we saw. But for some problems, that may not necessarily be an option. So at least you still have a generating function, even if Frobenius' method is not an option. Like, for example, what if the coefficients p and q, if they are not polynomials, then it becomes very difficult to apply Frobenius' method, because Frobenius' method depends on a power series. If p and q are not polynomials, we don't have like a power series representation of them. That makes things very challenging. Okay. So let's put this generating function to work. Suppose I set x equal to 1. Then I have 1 minus 2t plus t squared. That's a perfect square. So then I have a square root of quantity 1 minus t squared, so then I have 1 over 1 minus t. But 1 over 1 minus t is the sum of this geometric series. It's the sum of t to the n. So if I match this equation with this one, where x is equal to 1, what I have here is Pn of 1. But since the series I have is just t to the n, sum of t to the n, that tells me that Pn of 1 is equal to 1. So all of the Legendre polynomials are normalized so that when x is equal to 1, they're equal to 1. So they're not made orthonormal or anything like that. They're normalized this way. Next thing you do, suppose you take x and t and you negate them both. Well, the generating function doesn't change. It's because you have the negatives canceling out. But if I negate x and t in here, I'm going to get Pn of minus x times minus 1 to the n, t to the n. So if I match this series for g of xt to the series they get from negating both x and t, then by matching the t to the n's up, this falls out. So negating x multiplies the Legendre polynomial by minus 1 to the n. So what this means is, if n is even, Pn is an even function, meaning, so to refresh memory is what that means. Pn of minus x equals Pn of x. So in other words, negating x doesn't change anything. Whereas if n is odd, then it's an odd function. That means that Pn of minus x equals minus Pn of x. So negating x negates the function. It says even powers of x are even, odd powers of x are odd. And when you have an odd function, you plug in x equals 0, then Pn of 0 is equal to its own negative. So that means that when you have every odd function, it's always equal to 0 at x equals 0. It is no other option. So all the odd Legendre polynomials are 0 at 0. But when you have an even Legendre polynomial, you set x equals 0. So we go ahead and set x equals 0 in the generating function, and this is what we get. So what we can do is we can work out the power series of this function in t, and we get this binomial coefficient, really it's a generalized binomial coefficient, with t squared to the nth power, so t to the 2n. By comparing it to what you get by setting x equal to 0 in here, well, all the odd number terms are going to drop out because they're equal to 0 and x equals 0. All that's left are the even polynomials at 0 times t to the n. So you get this. So what that says is the value of the even Legendre polynomial at 0 has to be equal to this generalized binomial coefficient. But if you write out what this is, it ends up being equal to this. It's maybe double factorials. So to refresh your memory, this is equal to the product of all the odd positive integers up to 2n minus 1. So 1 times 3 times 5 up to 2n minus 1. Here, this double factorial is the product of all the even integers from 2, 4, 6 up to 2n. So now we've learned about the parity of the Legendre polynomials, what are equal to at x equals 0, also what are equal to at x equals 1. We can also figure out the coefficient of the leading terms, in other words, the coefficient of x to the n in Pn. So what I've done here is, if you mind a generating function, that can be written as 1 plus 2x, or 1 minus 2xt plus t to the n, t squared. Raised to the minus 1/2 power. So if I express this using the binomial theorem, again with the exponent of -1/2. So then you have these raised to the, each of these raised to the n power. Then, when we expand this, then we're going to have powers of -2xt times powers of t squared. So the largest power of x that can multiply t to the n is x to the n. You can have t to the n times x to the n. So we end up having this raised to the nth power when we expand this. So that means that we're going to get a term in here of this generalized binomial coefficient times -2 to the n, x to the n, t to the n. So the coefficient of x to the n in the nth Legendre polynomial is given by this. So this is so it's almost the same as this. It's just that instead of double factorial of 2n, we just have a regular n factorial down below. We still have the same odd double factorial up top. So this is the formula for the leading coefficient of each Legendre polynomial. Like it's not big enough. So this is what generating functions are for. Finding out fun facts about various sets of functions. That's the function of the Legendre polynomials knows what else. Different parties. Now, just like Bessel functions, the Legendre polynomials also satisfy recurrence relations. And you can find recurrence relations the same way as for the Bessel functions by taking derivatives of the generating function with respect to x or t. Now, I won't go through all the details here because it would be pretty painful and I'll probably screw it up. But if you take a derivative of the generating function with respect to t, and carry out some rearranging, then you get an equation of this form. That varies x equals 0, but notice we have different powers of t here. And what you'd like to do is perform index shifts on these so that you just have something times a infinite sum involving t to the n. Because when that is set equal to 0, that means that whatever is multiplying t to the n must also be 0. But because all the coefficients of the power series of 0 must be 0. And when you do that, this 3-term recurrence relation falls out. Now, all families of orthogonal polynomials satisfy 3-term recurrence relation. We saw the one for Chebyshev polynomials before. In other words, each polynomial depends on the previous two. Now, this is written in a weird way, but if I rearrange this, so Pn plus 1 can be determined from Pn and Pn minus 1. And that's very helpful for efficiently generating orthogonal polynomials, starting from the lowest degree on. Now, when you have a 3-term recurrence relation, you need the first two to start off. So the lowest degree Legendre polynomial is just 1. And the first degree Legendre polynomial P1 is x. So to get P2, you can just substitute P0 equal 1 over here, P1 equal to x over here, and then you can solve for P2. Actually, if I take this right here, and I'm going to set n equal to 1 throughout. So now, if I fill in P0 equal to 1, and P1 equal to x, now I have x squared there. Now I have 3, here, 2, P2 of x. P2 of x is equal to 1/2 3x squared minus 1. Now keep in mind, if you Legendre polynomials are normalized, so you substitute x equal to 1, you get 1. So sure enough, 3 times 1 squared minus 1 is 2, divided by 2, and we get 1. So then I can use P1 and P2 to get P3 and so on. If I take the derivative of the generating function with respect to x, then this is the equation I get. So now, if I were to distribute this through here, and so then I would get a few summations, and then I would form index shifts to have t to the n in every summation. Then I have this recurrence relation involving the derivatives of Legendre polynomials of different indices in terms of Pn itself. Although it's worth pointing out, if I were to take the derivative of this equation, so here I have Pn plus 1 prime, here I have Pn minus 1 prime. When I take a derivative of this, I need to use a product rule, so that would give me x times Pn prime, and then just Pn by itself. So that's another way to obtain this recurrence right here, just differentiating this one. So then I'll have just to make sure, because I feel like make sure that it really does simplify to that. So here I have xPn prime. Here I just have Pn. Here I have prime. Okay. See, we're not exactly the same. I may have spoken too soon, but okay. Now if I'm going to distribute everything. I think it would be equivalent. They all involve the same expressions. Okay. Something went wrong and tried to copy paste. Now, so for instance, here I have 2nx pn prime. Then I have 2n pn. Okay. So I take every term that has a factor n in it. Okay. So in terms of non-involving n, I'm going to evolve to the side. Then over here, I have two terms that depend on n. Okay. Now, this right here was multiplying n matches this. Now, if I look at multiplying n over here, I have 2x pn prime. And then I have 2 pn, which, yeah, it also seems odd. So it's almost like I have n times this recurrence plus some other things. So it's a digression I probably should not have embarked on. So if I'm going to move this out. I can take one of these and move them out here, and then so this right here, what's in here is everything from this recurrence relation. So presumably all of this must be 0. Because if I take this and move it to the other side, then I have all that equals 0. But then what I have left over is plus 1 Pn plus that equal that. And I'm checking to see if there is a certain number of recurrences that Legendre polynomials satisfy. And I don't recall if that is one of them. Oh, and plus 1p times xp prime. Oh, I'll be dang. Yeah. So, now we have this, the latter part of this equation. Copy it properly. Oops. So now we have this. That actually is one of the known recurrences for Legendre polynomials. So, in other words, I accidentally rediscovered that. Okay. So if I take the derivative of this one, we actually get 2. Better satisfied. Okay, so my original statement, I was thinking that this one could be obtained by differentiating this one. Sorry, this one, but that's not true. That because you also need to know this one to make it pull off that way. Okay, so there are other recurrences that I stated in the section that Legendre polynomials satisfy. You can find these are listed in the textbook. I just realized we're running out of time, but this is actually okay. If I take a generating function and substitute x equal cosine theta, then I end up with this that the 1 over square root that can be factored into this, and then I can take a Taylor expansion of function basically 1 plus x to the minus 1/2. If I use that Taylor expansion here and here, no, it's either the same, except here we have e to I beta, here we have e to minus I beta. And then I look at the coefficient of t to the n and what I get from multiplying these out, which is a bit of a mess. What you end up with is a representation of the Legendre polynomial evaluated cosine theta having this form, where all of these coefficients turn out to be positive. But the thing is, cosine is bounded by -1 and 1. So the largest thing that this expression can be is the sum of a and n. And if I set theta equal to 0 in here, I get Pn of 1 equals the sum of all these coefficients. But I already know that Pn of 1 is equal to 1. So the result of all this is that on the interval -1 to 1, the absolute maximum of the Legendre polynomial happens at x equal 1, and the maximum value is 1. Now keep in mind that Legendre polynomials are even functions when n is even. So if n is even, the maximum value of 1 is also occurring at x equal to -1 by symmetry. And it's odd, again, by different kind of symmetry. The minimum on this interval is assumed at x equal to -1, and the minimum value is -1. So, because Legendre polynomial, when the argument is between -1 and 1, can be expressed this way, that the Legendre polynomials are bounded, just as cosine is bounded by -1 and 1 everywhere, Legendre polynomials on the interval x between -1 and 1 are also bounded between -1 and 1. So having that boundedness property can be useful. At least you have some handle on its behavior, regardless of the degree of the polynomial. And of course, polynomials will grow very rapidly outside of that interval, but at least you have boundedness inside. This can be useful, for instance, certain numerical analysis applications where, well, a lot of times you want to know how large something can get. So at least you have a handle on that. Okay, now we have more to learn about Legendre polynomials in later sections, and we'll come to that soon enough. I think I should probably augment my notes with these other recurrence relations that are mentioned in the textbook or just not mentioned. These notes, yeah. But in the last, oh god, sorry, 3 minutes left. Wow, it's dark in here. Does anyone have any homework questions? Okay. Bunch of tiny ones.
Yeah.
Okay. Well, okay, let me get the book, the textbook. It's really dark in here.
Turn on the light,
Print our light. Okay, where we're looking. The technical one, the second one.
Which one can we be still?
Oh, that one, okay.
Something I want to do, but I don't know how to do it. Or if it needs extra information.
Oh, this one?
Yes.
Okay.
What are we supposed, like, compare with exercise 1.2.5?
Oh,
I assume which doesn't help going through.
let's take a look at that exercise. I have no idea what it is. Oh, where'd it go? Why did you know
1.2. You're on 1.3.
Yeah, but, oh, they split up the exercises. Usually we put them at the end of the section. Oh, okay, this.
What information are we supposed to get back?
Okay. Okay, when J is even. I'm not sure. Go back to the main problem here.
This does it tell us like we're supposed to only like look at the even part?
I think all we're really saying is that you have to get the same result as in that problem, because the answer in problem 125 is x strictly between -1 and 1, meaning it diverges when x is equal to plus or minus 1. But you're finding out the same thing here. So yeah, so I wouldn't say that it actually helps do the problem.
And also, so with the y odd, whenever the d-sets,
Yeah.
whatever, you apply that, and then you had like the helpful hint of like if the coefficient, like you take the like n over n squared, and the coefficient ends up being 1.
Yeah.
It ends up being 1 over n. Is that the can you only do that if like there's coefficients on the other side? Like if it's only if it's only just numbers on the other side? And it because I know on the even case it goes like
Yeah, yes, you can.
Okay.
Okay, so yeah, I'm having trouble deciphering.
This one, I am getting the extra 2 that's there.
Okay.
But then on this one, it was like the exact same thing on this side, and then just plus that and minus that.
Okay. Well, the thing is, you want to see what happens as n is going to infinity, and you think of lambda as a fixed value, so you can ignore it.
So it just,
Yeah.
okay. And so how do you know that, because I thought that test doesn't use as n is going to infinity because it's not in the notes like listed, but ratio test has it. Like,
Well, but it is for testing for conversions of conversions of a series.
so it still has that, like it should be in each step then?
Yeah, well, okay. So what you're doing is you're trying to express this as like 1 plus something over n. And well, the thing is, sorry, I need to see the expression one more time. You have, oh, okay, lambda there.
I made the answer still goes to that because on here it doesn't have like the limit that's still there.
Okay. But I guess another way to look at it is like your numerator and denominator are polynomials in n. And that to figure out, to write it as something over n plus lower order terms, you can think of lambda as being considered part of a constant term of those polynomials. So that's why it won't affect the result.
So I don't know if I can
Okay.
assume.
Yeah, you can, yeah. Because the key is dependence on n, and it's not.
Okay.
I want to make sure, does anyone else have a question?
Yeah.
Okay. Anyone in online land have a question? Okay, because then since we're 3 minutes past time, then if no one else has a question, I'll just say that the rest of you can go. Okay.
Thank you.
Okay, cool. I'll stop recording.